Hello and welcome to another science topic. Our focus today is the Big Bang Theory. And of course, I'm being silly. We're not going to actually talk about the TV show, but we are talking about the Big Bang Theory in terms of science. And we're going to connect what we've been talking about because we've been talking about wavelength information, stuff we get from space, and we're going to connect that wavelength stuff to this thing called the Big Bang Theory. If you're taking notes on the day this was assigned, it is the 19th. Otherwise, fill in whatever date it is that you are working. And go ahead and set up your focus notes so you've got this ready for future reference and review. And let's get into it. Our topic is Big Bang Theory. Oh, just another reminder, the only things you need to write down are the things in this color, this reddish brown. It'll give you the information that you need, but means you don't have to write down everything. All right, here we go. So the first thing I want to just kind of talk about is scientific models. When really important ideas are developed, there's usually three parts that go into those scientific models. There's someone who comes up with an idea or a model, and a model doesn't just have to be something that's built, it can just be a set of ideas used to explain something. So there's the new idea. So somebody comes up with a new idea. And then there's some existing idea that is like leading to the new idea or the new model or supporting the new model. Very rarely in science does just people come up with ideas out of nowhere. Usually, this is kind of the cool thing about science is that it's really collaborative. There's something from, history or something that somebody else figured out in a different country that somebody else is like, "Hey, that makes me think of this idea," and then it builds off of it. And then there's usually some experimental evidence. This is what makes science stand out from lots of other places where people come up with ideas, is that there's theory behind it. That would be like maybe the existing ideas or the support. And then there's also experimental evidence. That is huge. So that is a big deal in the science world. So what we're going to do today is we're going to look at the development of the scientific idea that we know as the Big Bang Theory. And the thing that's really cool is that the Big Bang Theory was developed in a couple different ways that agree with each other, which in science is like, wow, that's like so amazing. When you can get two different kinds of lines of logic that support the same idea, it makes us pretty confident that that idea has been proven, even though we still call it the Big Bang Theory. That's our focus for today. So, the Big Bang story, the purpose of this story that I'm going to tell you, because I'm kind of going to give you all the different actors and characters and ideas that go into this thing called the Big Bang Theory. So, the purpose is to answer this question. Well, what is the Big Bang Theory? What does it say about the universe? Who were the important scientists that helped develop the Big Bang Theory? How did they come up with the Big Bang Theory? And then why is this considered such a big deal? So those are kind of like our more essential questions. So like lots of reasons that we talk about the Big Bang Theory, that it is really one of the biggest science ideas of all times. There's actually a book out there that's like the 5 big ideas in science, and Big Bang Theory is one of those 5. Like if we had to pick just 5 big ideas in science, the Big Bang Theory is one of them. All right, so with all of that hype, let's get into it. So we need to have a starting place. So the first thing we just talk about is, well, what is the Big Bang Theory? When people use that term, what are they really talking about? And what it is it's a set of ideas of how the universe changes over time. That is what the Big Bang Theory is. That's all. How is the universe changing? That's what it's trying to answer. And then what are some things we know that kind of lead into the Big Bang Theory? So first of all, it explains that the universe is expanding. That's a really big deal. Originally, the universe was small, dense, and hot. So, based on the stuff that we have evidence of now, we can support that idea that originally the universe was small, dense, meaning it was really, really packed together, and it was really hot. The universe began to cool because it was expanding. So think of like if you had a really, really hot marshmallow, but it was really, really hot in the fire, but then you spread it out. As it spreads out, it would be cooler because that energy kind of spreads out instead of all being in one spot. So the universe began to cool because it was expanding. And then over time, matter was created from energy. This is the part that sounds a little bit harder to kind of explain. The universe is space and time. So that means that space and time are created as the universe expands. And again, this is one of those just kind of like wild ideas, but we have support of this in science. So it's not just a made up random theory. It is based on evidence, and I'm going to give you sort of the science behind it to help you understand how the universe has changed over time. That's really what we're focusing on. That's our starting place. Okay, so let me give you kind of a visual. So we've got this wherever the dawn of time was, like wherever everything started, in a tiny fraction of a second. Then you've got these particles, and then thousands of years later, you have more different kinds of particles. And then this long, you have the universe the way we picture it now. So there was just a tiny moment when there was nothing, and then now there was something. And then over billions of years, we come up with the universe the way we have pictures of it now, with stars and planets and galaxies and things like that. So that's just kind of a visual of our Big Bang Theory. The other thing that we are not, that people sometimes ask, but what we're not going to talk about today is, well, what happened before the Big Bang? Well, here's the thing. Our physics does not allow us to predict it, so we don't know. So that part you would have to fill in based on your own ideas or other ideas that are out there or things you talk about with your family. So we don't have an answer to that in science because our knowledge of physics doesn't allow us to predict before. So we can start here. So based on the data we can collect today, it goes back this far. Before that, we don't know. We don't have an answer for that. So that's one of those things I can't help you with, but I can help you understand the Big Bang Theory. All right. Go ahead and take kind of a break so far and just think about what we've talked about so far and do a level 1 kind of question. Something you get right from the notes, keywords like list, or, list the things we know about the Big Bang Theory or about the universe, or describe how scientific ideas start, something like that. So just to kind of give you a level 1 kind of question, just kind of think about what we've done so far. All right, let's keep going. So now that we've got kind of the background around idea of like what this Big Bang Theory is, let's figure out where it came from. So a historical start. There's 2 big thinkers we need to give credit to, and they are Aristotle, so an old philosopher, so Greek philosopher, but then Isaac Newton, who was more of a modern kind of scientist. They both believe, so even though they studied things hundreds of years apart from each other, they both believe that there's absolute space and absolute time. However, modern scientists started thinking about this and they disagreed with this idea of absolute space and time. They said that it was more like relative. So, relative space and time due to everything already moving. And the best way I can explain this would be like driving in a car. If you're riding in a car and you just look at your body, nothing else, you just look at your body, you would say, oh, my body's not moving right now. It's just sitting here in this car. But then if you look outside this window, this is where you'd be like, wait a second, my body is moving. I can see things moving past me. I can, maybe you even hear noises like go away from you. So that relative. So if you only compare your body to itself, like your hands sitting in your lap when you look at yourself in the car, that would say that, oh, nothing is moving. But if you compare it to something relative, so you look outside at the trees moving past or other cars moving by or buildings that are going by you, that's how you know that relatively you are in motion. So that's just kind of an analogy of kind of thinking of this idea of relative. Because everything is moving around you, you can decide that you are moving. That's just one analogy of that relativity idea. So the first line of development, go ahead and write that down. The first line of development actually starts with Einstein. So in like the, kind of early 1900s, he came up with this theory of relativity, and he's using that theory to try to explain how gravity works. Well, one result of his theory of relativity is that the universe must be expanding. But here's the thing. Einstein's work is so complicated. There is no way for me to understand it and explain it to you right now. It is so beyond my level of physics knowledge. And so I'm just mentioning it because the thing I do want to talk about is related to Einstein. So Einstein, big thinker, super creative, super imaginative. So lots of big ideas, but we're actually not going to focus on his work, but his work is related to somebody else I do want to talk about. So I want to talk about this guy, Georges Lemaitre. That's my attempt at a French accent, which I can't do very well. Anyway, so Georges Lemaitre, a little bit after that theory of relativity became pretty well known, he proposed something called the primeval atom theory. So like kind of like the basics of atoms is kind of what he's thinking. And atoms is maybe a word you've heard of. Basically, it's like the particles that make up everything in the universe. So this is what he said. His theory says that the universe started as a small single point and expanded. From that moment on, when the universe was a small single point, the universe has been expanding and is still expanding. And his work is really based on the theory of relativity. So I'm giving weight or support to Lemaitre's idea because it's upon the work of Einstein, who is an established scientist that we have heard of. And so, kind of that idea of like this new theory has support from past information. So, Einstein's work that was readily accepted in the science world, Lemaitre's idea was based on that. So he was using the theory of relativity to come up with his idea called the primeval atom theory. Okay, so that's a big idea, but it's still, I really haven't proven it to you, right? Because it's just his idea based on some other idea that I didn't explain. So I got to give you some more depth or support of why do we believe Lemaitre's idea is, why do we conclude that it's true? So some more information. Around after Lemaitre's time of publishing this primeval atom theory, then there was like better technology. So we were able to see stars and galaxies out there much better. And one of the guys who did a lot of work on this was Edwin Hubble. So Hubble now, instead of it just being theory, Hubble can actually see stuff and take data. And that was a big deal. Because remember, if we can look at parallax of stars, so using really good telescopes that are looking at things really far away, we can use parallax to determine the distance of stars. And remember that we can measure wavelength and redshift to determine speed. So wavelength of the star divided by wavelength in the lab times the speed of light minus 1. We do all of those calculations. So we can figure out distance and we can figure out speed. So Edwin Hubble, go ahead and jot his name down now. So Edwin Hubble took Lemaitre's idea, and Hubble was able to get actual experimental evidence. It's not just a theory anymore, but he was able to use data to figure out, use his advances in technology to figure out the speed and distance of galaxies, and then graph it like you just did the other day in class in that assignment. And so by observing light from the galaxies, Hubble now had actual experimental evidence. It's not just a theory anymore, but he had this idea that galaxies are moving away from each other and that the speed varies with the distance. The further the distance, the faster the galaxies are moving. So this is Lemaitre's idea that the universe is expanding, has now been proven using evidence because of the work that Hubble did. So again, we have the idea, the theory behind Lemaitre's idea based on Einstein's ideas, but then now Hubble is actually giving us evidence to support it. So it's not just random thoughts or even thoughts that are really smart. It's thoughts that now have support of actual measurements and data to back it up. And that's a huge thing in science. So we get really excited about that. So good job, Hubble. And then the last piece of this is, since we're trying to talk about how the universe has changed over time, we want to know kind of where the universe started. So what we can do is we can take a certain galaxy, right? And we can figure out the speed of that galaxy. So we've got this number. We can figure out the distance to that certain galaxy. And since we know that we have the speed, and we know the distance, we can now solve and we can do some algebra, right? So since this is a math equation, we can change this around and solve for time. And then we can plug in distance from here, speed from here. So then now we get this, right? So time is equal to distance divided by speed. That came from this equation. And then if I plug in my two things from this graph, I get that the time of the universe expanding has been 1.5 times 10 to the 10 years, or 15 billion years. So that's where that number comes from. It's from things we can actually measure: speed of galaxies and distance of galaxies. We can use the math equation or a chemistry or science or physics equation that speed is distance over time, like miles per hour is speed. We can solve for time because we have distance and speed from our wavelength data. And then now we can say that the universe has been expanding for 15 billion years. So giving us a pinpoint of when that Big Bang happened. But again, we can't go before that. So let's summarize what we just learned. Einstein had a theory about relativity. Lemaitre used that theory of relativity to come up with a kind of a model of the universe origin. How did the universe start? And then Hubble backed it up, and all of it leads to the Big Bang theory. So that's, again, kind of this cool way of like all these different ideas all came to that same conclusion. And in science, that's a big deal. But we're not done. There's another completely new set of ideas that also support the Big Bang. So that's what we're going to talk about next. First, though, do your second brain break. So kind of think about what we've talked about so far and what could you do for a level 2 kind of question. Maybe sketch the timeline of the Big Bang Theory, or criticize, point out something that you think doesn't seem to make sense, or explain how Lemaitre and Hubble came to the conclusion that the universe is 15 billion years old. Something like that. Level 2 brain break. Go ahead. All right, let's finish this up. What's our second line of development? The first one was Einstein's relativity, Lemaitre's primeval atom theory, and then Hubble's experimental evidence. So what's the second line of development? Well, we're still going to talk about Georges Lemaitre. His primeval atom theory has another prediction. So it's another part of the theory that not just that the universe is expanding, but that the initial super hot Big Bang, the universe should be cooler after that. So first there was that Big Bang moment 15 billion years ago, and then now when the universe is expanding, it should cool down. So other scientists were studying that idea that when something expands, it should cool. So the next line of development is based on existing observations, models, and experimental evidence of how wavelength is related to temperature. So again, we've talked about wavelength, we've talked about temperature in terms of things we can measure from space. Now we're going to put that all together and end up with the same conclusion for the Big Bang Theory. So Robert Dicke, yep, that's his name, uses the physics laws of expansion and cooling. So this is an established idea at the time, that physics, that as something expands, it cools. So that's a law of physics that has been established. And so Dicke uses that to predict the temperature of the universe. And so if there has been 15 billion years, so if that's true, if the universe has been expanding for 15 billion years, then most places in the universe should be 2.7 Kelvin. Now, remember, we said that the sun was like 5,000 Kelvin. So that doesn't seem to be figuring things out. But remember, we're talking about the universe, not just one specific piece, not just one specific star like the sun, but the prediction of the universe should be 2.7 Kelvin. Well, there was a guy, Wayne, so that did a bunch of this. So Wayne's law, which is temperature versus wavelength. And so if you measure the temperature of something, you can figure out the wavelength. So if the temperature is 2.7, so that's of course way down on this graph, you can figure out what the wavelength would be. And the wavelength would be really, really, really long. Because notice this, when the temperature is high, the wavelength is short. Well, that makes sense because a lot of energy in that temperature would mean a really, really, really small wave that is repeating itself really, really fast, high energy. So then if you have a really, really low temperature, like way even lower than this graph is showing, we can predict that the wavelength would be like way over here. And this wavelength is 8,000 angstroms, which is something that is used to measure really small pieces of data, that the wavelength would be really, really long, even to the point of microwaves. So microwaves is what we would be mostly measuring in the universe. Okay? Now, this is all scientific ideas, but it's still a prediction. So it's a theory that makes sense. There's lots of things to support it, but we don't have any evidence yet to prove that that temperature is 2.7, to prove that it's microwaves. Well, that's where our last guys come in. And this actually was totally an accident. So here's the last thing. Penzias and Wilson figured out something called the cosmic microwave background experiment. And that proves, it's the evidence that Dicke's prediction of the temperature was accurate. It was correct. So in the 1960s, Penzias and Wilson, they were actually working for Bell Labs, a telephone company. And what was happening is that phone company was trying to make like satellite calls, like in the 1960s. And they kept getting this static on the phone calls. And so they called Penzias and Wilson to try to figure out like what was going on. So you can see them with kind of like a satellite here. And it turns out that that static that was like messing up the phone calls and making them think that the phone calls were staticky and not clear was actually picking up microwaves from space. So the cosmic background in space is microwaves. Well, that was what Dickey predicted, that if there was microwaves, then the temperature should be 2.7, and it supports itself. And then it turns out that Penzias and Wilson got the Nobel Prize for it, even though it was like accidental experimental work. It was huge because it again supported the Big Bang Theory in a totally different way. So let's go ahead and add on to that. So let me go backwards. So if you were like, well, wait a second, if it was an accident, like how can we be so sure of it? Well, here's the thing. Since the 1960s, so Penzias and Wilson's data was significantly confirmed from an actual telescope that measured wavelength. And then also, even as recently as 2002, there was even more satellites that showed some details about temperature from space. So it wasn't even just way back in the 1960s. This still has been confirmed in the 80s, in the early 2000s. All of it supports the same idea that Dickey figured out way back when. So again, we've got this kind of like three-part thing. We've got the theory behind it using physics. We have the Robert Dickey model based on Lemaitre's model also that says that the universe should have cooled after the Big Bang. And then we have the experimental evidence all leading to that same singular moment of that Big Bang theory about 15 billion years ago, and supported by wavelength data, which we've been talking about this whole unit, to sort of help us understand how the universe has been changing over time. That is the cool thing about the Big Bang Theory, is that it's supported in lots of different ways with lots of different scientific ideas. And again, the whole purpose of the Big Bang is just to help us understand how the universe is changing. All right, so now let me give you a couple visual things. So imagine this. So the Big Bang Theory lasted, or the Big Bang, sorry, lasted this really tiny, tiny moment. And then the universe started shaping. And then when the universe was 3 seconds old, that is when elements started forming. And then it took thousands of years for there to be sort of radiation and light forming. And then hundreds of thousands of years when matter started forming. And then millions of years, and we have galaxies. And then our sun was about 5 billion years after the Big Bang. And then we've got life that forms about 3.8 billion after that. And then we get 700. This is years before present. So 5 billion years ago from today was when our sun was born. 3.8 billion years from today ago, if that makes sense, was when life was starting to form. Animals, mammals, dinosaurs, people. And then only about 170,000 years ago is when that 1987, it's called 1987, a supernova has exploded. And then we go forward. So then now we have another supernova. And then we've got Newton's, and then we have Einstein, and then we have Hubble. And starting to get into now, so around the 90s, is when the Hubble telescope was actually repaired so that it could keep being used. So the Hubble telescope was launched in 1990s. That was when we were able to confirm the Big Bang Theory. And then Hubble telescope repaired. And so now going into the future, will there be a time where the stellar era ends and other black hole era begins and the dark era begins? Now this is, billions and billions of years into the future. But based on what we know now, that the Big Bang happened about 15 billion years ago and that universe just kept expanding and cooling, will it get to the point where our universe will be so expanded and cold that life like we know it can't exist? And that's just kind of getting into some more, there's some astronomy to thinking, but kind of like science fiction. But for now, it's fiction. Maybe it won't be in the future. All right, and then that brings us to the end of our our last level 3, so our last brain break. And so now you could do some really cool level 3 questions with imagine or predict. So imagine what will the universe will be like in 100 million years, or predict what will happen when the sun burns out, or different things, or defend the Big Bang Theory. Big Bang Theory, sometimes people attack it. So defend it. That would be a great use of your thinking skills. All right. And then that brings us to our summary. So we did our Costa questions. We have our new information. Your special summary for today is something to summarize the Big Bang Theory, obviously, but you're going to do something called an acrostic poem. An acrostic poem, put this on an output page, is one of those where you put a word or something down the side of the page. So put the words BIG, BANG down the side of your page on an output page. So next to this page where you're taking notes. And then what you do is each line starts with a letter. So the letter B starts this sentence, and the letter I starts this sentence or this word, and the letter G starts this sentence. And there's no rules about how many words you put in each line. You could put one word, you could put a whole sentence. But the whole point is that after you read this poem, that each line starts with one of the word letters of Big Bang, it summarizes today's notes. So somewhere in there, like you've got different parts of our notes that start with B's, different parts of our notes that start with I, different parts of our notes that start with G, and it kind of reads like a story or a poem that summarizes the Big Bang Theory. So it's just a creative way to kind of do our summary, a little bit special. So you have to think about it in a little bit different way. It helps your brain stretch a little and grow and learn instead of just doing a normal summary. And that brings us to the end. So your to-do list. Go back and finish any Costa questions, write your Big Bang acrostic poem summary, and then you're going to take a picture of that poem and post it in the media album for today so that other people can see it. And me looking at those posts is part of how I'm going to take attendance today too. So make sure that you check on that, write your summary, just to kind of summarize the stuff that we learned today. And then that's it. We'll see you at our next Zoom session. Thanks so much for exploring the universe with me. We'll talk to you later. Bye.